Hey everyone, and welcome back. Today we're going to talk about something that sounds like it's straight out of science fiction, but is happening right now in a lab in New Zealand. We're talking about bottling a star, creating a miniature sun on Earth to generate nearly unlimited clean energy. This is the story of nuclear fusion, and specifically, a wild and brilliant approach that takes its inspiration from the planets in our own solar system. So, first things first, what even is nuclear fusion? At its heart, it's the process that powers our sun and every other star in the universe. In the simplest terms, you take two very light atoms, like different versions of hydrogen, and you smash them together with so much force that they literally fuse into one, creating a new, slightly heavier atom, like helium. Now, here's the magic part. The new helium atom that you create actually has a tiny bit less mass than the two hydrogen atoms you started with. That little bit of lost mass doesn't just disappear, it gets converted into a huge amount of energy. And when I say huge, I mean huge. This is all thanks to Einstein's famous equation, which tells us that mass and energy are two sides of the same coin. The fuel for this process on Earth would be two isotopes of hydrogen called deuterium and tritium. And the amazing part of all of this is that deuterium is incredibly abundant. You can extract it from regular seawater. Tritium is a bit rarer, but you can actually breed it from lithium, which is also a very common element found all over the world in the Earth's crust and in seawater. This means we'd have enough fuel to power the planet for thousands, if not millions of years. The energy density is just staggering. 1 single kilogram of this fusion fuel could produce the same amount of energy as 10 million kilograms of fossil fuels like coal or oil. To put that in perspective, a big 1 gigawatt fusion power station enough to power a city would need less than a ton of fuel to run for an entire year. And the benefits are just as massive. The only byproduct of the main fusion reaction is helium, which is a harmless, inert gas. There are no carbon emissions, no greenhouse gases. And unlike current nuclear power plants which use fission, splitting atoms apart, fusion doesn't produce any long-lived radioactive waste. Plus, it's inherently safe. The conditions needed for fusion are so extreme and difficult to maintain that a runaway reaction or a meltdown is physically impossible. If anything goes wrong, the reaction just stops. So, unlimited fuel, massive energy output, and it's clean and safe. It's the ultimate energy dream. Of course, if it were that easy, we'd have done it by now. The reason we haven't is because of one gigantic challenge: creating the right conditions. To get those atoms to fuse, you have to overcome the immense natural force that pushes them apart. The way to do that is with temperature. Extreme, mind-boggling temperature. We're talking about getting a gas hotter than the core of the sun over 100 million degrees Celsius. The sun can get away with being a bit cooler because its immense gravity creates crushing pressure at its core, helping to squeeze the atoms together. Here on Earth, we don't have that luxury, so we have to compensate with even more heat. When you heat a gas to these temperatures, it transforms into the fourth state of matter, which is plasma. This is a super hot, electrically charged soup where electrons are stripped away from their atoms. It's what stars are made of. And it leads us to the central problem of fusion. No physical material on Earth can possibly contain something that's 100 million degrees hot. If that plasma touches the wall of any container, it will instantly cool down, killing the reaction, and it would vaporize the wall in the process. So, how do you hold a star? The answer is with a magnetic bottle. Because plasma is made of charged particles, it can be controlled and shaped by powerful magnetic fields. The idea is to create a magnetic cage that holds the super hot plasma in the middle of a vacuum chamber, suspended in place so it never touches anything. To get to net energy gain, you have to hit what's called the fusion triple product. You need the plasma to be at a high enough temperature, at a high enough density, and you need to hold it all together in your magnetic bottle for a long enough confinement time. Getting all three of those things right at the same time is the great challenge of fusion energy. For decades, the main approach to building this magnetic bottle has been a donut-shaped machine called a tokamak. But today, we're talking about a different idea, one that came from a moment of cosmic inspiration. The story starts back in 1986. A physicist named Akira Hasegawa was looking at data from the Voyager 2 spacecraft as it flew past the planet Uranus. He noticed something really strange and wonderful about the magnetospheres of planets like Uranus and Jupiter. A magnetosphere is basically the giant magnetic bubble that surrounds a planet generated by its core. What Hasegawa saw was that these planetary magnetospheres are naturally really good at trapping plasma. They create these profiles where the plasma is incredibly dense and hot right in the center. But the most surprising part was why this was happening. It wasn't happening in some perfectly calm, stable environment. It was being caused by turbulence, stirred up by the constant stream of particles from the sun, known as the solar wind. In this natural system, turbulence wasn't causing the plasma to leak out. It was actually doing the opposite. It was pushing the plasma inward and concentrating it, a process called a turbulent pinch. This was a radical, counterintuitive idea. In most fusion reactor designs, turbulence is the ultimate enemy. It's one of the main reasons plasma escapes the magnetic bottle and cools down. Engineers spend all their time designing incredibly complex magnetic fields to try and stamp out every last bit of turbulence. Hasegawa's idea was to flip that completely on its head. What if, instead of fighting turbulence, we could build a machine that mimics a planet's magnetic field and actually uses that turbulence to our advantage? What if we could build a reactor that works with the natural physics of plasma instead of against it? That brilliant idea from space eventually led to a real-world experiment on Earth. In 1997, a joint team from MIT and Columbia University decided to build a machine to test Hasegawa's theory. It was called the Levitated Dipole Experiment, or LDX. The machine itself was pretty impressive. It was housed inside a huge 16-foot diameter vacuum chamber that was shaped a bit like a squashed pumpkin. At the heart of it was a half-ton, donut-shaped superconducting magnet about the size of a big truck tire. To truly mimic a planet's magnetic field, this magnet couldn't be held in place with physical supports, because any support structure would touch the plasma and ruin the confinement. It had to float. So, they levitated it. The half-ton magnet was suspended in the middle of the chamber by another powerful electromagnet located overhead. A sophisticated computer control system used 8 laser beams to constantly track the magnet's position and keep it perfectly stable, to within half a millimeter. Then came the critical experiment. The team ran the machine in 2 different modes, once with the magnet held in place by physical supports, and again with the magnet fully levitated. The results were stunning and proved the theory was right. As soon as the physical supports were removed, the plasma confinement got dramatically better. The turbulent pinch kicked in, just as predicted, and the plasma density became sharply peaked in the center, creating a hot, dense core exactly like the one seen in the magnetospheres of Jupiter and Uranus. It worked. But while LDX was a huge scientific success, it had its engineering limits. The magnet was made from what are called low-temperature superconductors, and it had to be charged up using induction from a coil below it. This meant it could only run for about an 8-hour period before it had to be docked to be recharged. That's fine for an experiment, but it's not a viable path for a power plant that needs to run continuously, and so, after proving the physics, the project eventually shut down. For a while, it seemed like this incredible concept might just be a fascinating footnote in the history of fusion research. But now, the idea has been revived, and it's being pushed forward by a new team with new technology. Enter OpenStar Technologies. They're a private fusion startup based in Wellington, New Zealand, that spun out of a research institute famous for its world-leading work on high-temperature superconducting magnets. They've looked at the promise of the levitated dipole, and they've built the next generation machine to take it to the next level. It's called Junior. Junior is designed to be an LDX scale device, meaning it's about the same size and has a similar mission, to replicate the amazing physics results from LDX, but to do it using cutting-edge technology that simply didn't exist a decade ago. And this isn't just a new group picking up an old idea. There's a direct line of expertise connecting the old project to the new one. The director of plasma science at OpenStar is Darren Garnier, who was the chief experimentalist on the original LDX project. This continuity of knowledge is incredibly valuable. It also signals a really important shift. The levitated dipole concept has moved from the world of academic, government-funded research into the fast-paced, milestone-driven world of a private company aiming to build a commercial product. That focus and urgency could make all the difference. So, what makes Junior such a big step forward? It all comes down to the technology under the hood. The vacuum chamber is about 5.2 meters in diameter, similar in scale to LDX, but the heart of the machine, the floating magnet, is a complete game changer. It's a powerful superconducting magnet with a field strength of about 5.6 Tesla. But crucially, it's made from a material called REBCO, which is a high-temperature superconductor, or HTS. This is a massive upgrade. HTS magnets are more robust and can operate at warmer temperatures than the old low-temperature ones, making the whole system more efficient and resilient. But here is the single biggest breakthrough, the technology that really unlocks the potential of this design. Junior integrates a brand new HTS power supply directly on board the floating magnet itself. Think about that. They have figured out a way for the levitating magnet to generate and maintain its own powerful electric current wirelessly while it's floating in the vacuum. This technology, sometimes called a flux pump, completely solves the biggest engineering problem that held LDX back. There's no need to dock the magnet to recharge it. It can, in principle, run continuously. This is the key innovation that could turn this concept from a brilliant physics experiment into the actual blueprint for a working fusion power plant. To get the whole process started, they heat the gas inside the chamber using less than 50 kilowatts of power from something called electron-cyclotron resonance heating. It's basically like a very, very powerful and precise microwave oven. All of this incredible engineering has already led to a huge success. In late 2024, the OpenStar team completed their first experimental campaigns with Junior and achieved first plasma. This is a fundamental milestone for any new fusion device. It's the moment when all the complex systems, the vacuum, the magnets, the cooling, the heating, all work together for the first time to create that initial ball of superhot plasma. This is the "it works" moment. The next major step for Junior, planned for 2025, is to conduct experiments with the magnet fully levitated. This is when they'll aim to reproduce those critical plasma confinement results from LDX and show that the turbulent pinch works just as well, or even better, with their new and improved hardware. But OpenStar is already looking further ahead. They have a clear roadmap, and the next machine on that map is called Tahi. Tahi is designed to be the device that takes this concept all the way. The goal for Tahi is to achieve the Lawson criterion. The Lawson criterion is essentially the scientific break-even point for fusion. It's the point where the combination of temperature, density, and confinement time is so good that the fusion reactions in the plasma are generating more energy than you're pumping in to keep it hot. Hitting this target is the final scientific hurdle you have to clear before you can start designing a real, commercial power plant that puts electricity on the grid. This Junior to Tahi strategy is a smart, iterative approach. Junior is the technology demonstrator, proving that the new HTS magnet and onboard power systems work as designed. Once that technology is de-risked, Tahi will be the performance demonstrator, built to push for the record-breaking plasma conditions needed for net energy gain. And that's the story of how looking at the magnetic fields of distant planets might just be the key to unlocking unlimited, clean energy right here on Earth. The journey is far from over, but for the first time in a long time for this incredible idea, the path forward is looking clearer than ever. And that's a wrap for today. It's a pretty wild story, right? Taking inspiration from the planets to build a star on Earth, we'll be keeping a close eye on OpenStar and their journey. If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.